Okay, so thank you for inviting me. So what I'm going to focus on today is GW 170817, the discovery of a binary neutron star merger. So I'm going to split this talk into two parts. The first, I'm going to talk about the story of the discovery of 170817. You hear a lot tomorrow about the multi-messenger discovery. And then in the second part of the talk, I'm going to talk about some of the results that my group has on the inclination angle of the binary and testing the nuclear equation of state that's worked with Ido Berger and Jim Latimer. So this is the nice plot that shows the masses in the stellar graveyard. So this is solar masses of the compact objects here. These small objects down here are the neutron stars have been detected using electromagnetic waves. The purple circles here are black holes detected using electromagnetic waves. And then the light blue up here are the LIGO and Virgo binary black hole merger signatures. What I'm going to focus on, I think Ben Farr is going to focus on the binary black holes in 01 and 02 in his talk tomorrow. What I'm going to focus on today is this one down here, which is the merger of two neutron stars to form something. We're not quite sure what, so there's a little question mark right there as to what the end product is. And there will be some talks on that as well, I believe, tomorrow. Okay, so this is in the anatomy of what a discovery looks like. This is how we discovered 170817, the binary neutron star merger. I say we, when I did this, some of you may know, I was a LIGO scientific collaboration member for almost 20 years. I left in February. This is last year when I was still a member of the collaboration. So this is work done by the LIGO and Virgo collaboration. And the discovery of the binary neutron star merger started this is UTC. So this is 8:47 Eastern time on the 17th, when we have these codes that run, and these are, Alessandra talked a bit about the waveforms and the templates. This is a templated-based search. So what this does is there's a piece of code called GST-LAL. It's a low-latency search developed by Kip Cannon and Chad Hanna. Primarily, this basically searches through the data, looking for waveforms in the data that match a set of template patterns described by binary neutron star mergers down from one solar mass, component solar masses, so 1, 1, at the bottom end of where we search for neutron stars, all the way up to as high as we can go before the waveforms start to disappear into the noise, up to a couple hundred solar masses. So this is a low latency search that is run 24/7, looking for anything that pings in the detected data. And if the searchers see anything, they generate an alert that comes to us via email, cell phone, et cetera, et cetera. So on the morning of the 17th, there was an alert generated. So the event was submitted at 8:47 EDT. So this is the first notification of the alert. It happened a little bit later after the event happened because there was some data hangups in the data processing. Those have since been corrected. So it wasn't seconds afterwards. It was tens of minutes afterwards. So the event was submitted at 8:47 EDT, and this got everyone's attention. Why did this get everyone's attention? Well, one of the things the searchers do is they measure the false alarm rate. There's a lot of noise in the LIGO detectors. So Lisa talked earlier about the noise curves that you see when you see the LIGO spectrum show you the majority of the noise, which is the stationary noise background in the detectors. So that's the noise from the fundamental sources in the LIGO detectors. There's also a lot of glitches, pings, bangs, non-Gaussian stuff, variation in the noise, that it's the search pipeline's job to try and separate the signal from the noise. So these things run through. They have all kinds of signal processing techniques that you can ask me about later that try and separate what are clear signals from what is the noise. And their primary job is to measure the false alarm rate of these signals and to see how long you would have to wait for a piece of noise just to give you a fluctuation that looks like this signal. So this thing came out, and it looked significant with a false alarm rate of about 1 in 9,000 years, which is not incredibly high. It's not the 200,000 we got for the binary black holes, but 1 in 9,000 years is a pretty significant event. I'll talk about why it wasn't more significant than that initially. So the other thing that then drew our eye is the high signal-to-noise ratio. So in perfectly stationary Gaussian noise, if the LIGO detector is behaving well, the average signal-to-noise ratio is about 2. And it falls off as e to the minus rho squared. The significance falls off as e to the minus rho squared. So this thing came out with a signal-to-noise ratio of 14. This is incredibly significant in the detector data. So we have a 1 in 9,000 years and then an SNR of 14. The other thing we get reported very quickly is a mass estimate for the signal. So this is signal-to-noise ratio. The other thing we get reported very quickly, because the templated searches grid up the space by masses of the binary, so they can report a rough estimate. It's not the precise parameter estimation, but they report a rough estimate of the masses of the binary. And this signal came out with a loud SNR and a low mass. So the low chirp mass, which is the combination of the masses that enters in the leading order phasing of the binary, was 1.2. Low total mass, so M1 plus M2, the sum of the component masses, 2.8. If you divide 2.8 by 2, you get 1.4, 1.4, which is pretty much what you would expect for two binary neutron stars. So this very quickly suggested a binary neutron star analysis. But, I should say, and there's a Fermi gamma ray burst event 2 seconds after the merger. So the Fermi satellite, the GBM on the Fermi satellite, pushed an alert into our system that said there's a Fermi gamma ray burst event 2 seconds after the reported LIGO merger time. So this starts to get very, very exciting. We have a loud signal, low mass, and a Fermi GBM GRB alert 2 seconds after the 2 seconds after the discovery of the event. But the search was reported only in the LIGO Hanford detector. So the reason this significance is only 1 in 9,000, only 1 in 9,000 years, is that the initial event identification from the low latency searches that run without any human intervention, they only saw this signal in the Hanford detector. And with one detector, you can't really do side localization. So we realized very, very quickly we had something incredibly special on our hands, but the low latency searches only picked it up in the LIGO Hanford detector. So what happened is the humans started to get involved. Everybody leapt on a telecom, started looking at this data and trying to figure out what was going on. Now, I've worked on the detector characterization, the searches for a long time, and kind of between initial and advanced LIGO, one of the things I always tell the students in my group is, we're really going to have to pull these binary neutron stars out. It's not like a binary black hole signal where you've got a lot of SNR and a small time frequency volume, and you'll just see these things as a blob as a blip in a time frequency data. We're really going to have to work to pull these things out. And so the first thing we did after looking at this screen is we looked at the automatically generated time frequency spectrograms of the LIGO data, and lo and behold, you see this beautiful track right here without doing any processing whatsoever. This was just produced by the machines that automated the processing of this signal. So this is time on the x-axis, gravitational wave frequency on the y-axis, and you can see the figures from the paper that I'll show in a second have some more human cleaning done to make it stand out better, but this is without any human intervention whatsoever, just the machines pulling out this signal. You see this beautiful track that looks exactly like the track you'd expect for a binary neutron star merger. So this is the signal in the raw signal in the LIGO Hanford detector. Okay, what about LIGO Livingston? This is what you see when you look at LIGO Livingston. And there are two things you can see in this time frequency spectrogram. The first is you can actually see the track of the merger right here. You can actually see a bit better in the Hanford data than you can in the Livingston data, because the Hanford instrument was actually more sensitive than Livingston. But you have this giant thing right here, smack bang towards the end, a second or so before the merger of the event. And this is what stopped the automated pipelines from finding a multi-detector signal in low latency. So this is a glitch that happened in the detector data. So this is a short duration noise transient. This is one of these things that happens periodically, happens in the LIGO detector data, and is one of the primary things the search pipelines have to deal with. So sometimes the search pipelines deal with these automatically. In this case, it didn't. And so the humans had to get into gear and try and mitigate the effect of this noise transient right here and see if we could pull something out of the data in order that we could get a signal in the network, in the two LIGO detectors and in the Virgo detector. With a signal in the three detectors in the network, we can figure out where on the sky it is, and we can start telling people to point telescopes. But we didn't sit on this for long. We sent out an alert. Immediately we had this. We knew that we had a binary neutron star signal in the data, and so we immediately started sending out alerts to the astronomy partners, going out via these GCN system that's set up, and then a bunch of people started texting their astronomy partners. So this was 9:07. It went out. This is a text message to an astronomy colleague of mine who may be in this room. Said, go, check your email. This is the alert that went out. Coincident BNS. We knew we had a BNS extremely quickly. The astronomy community reacted, said, can I call you later? I'm stuck on a telecon. Said, hope it's a decam telecon. The astronomy community leapt into action, but they had a few hours to get ready because at this point we didn't have a sky localization. So at this point we knew we had a BNS on our hands, but we didn't have a sky localization. So what did we do? So this is an image from the discovery paper that shows how we handled this in low latency. And we had some such techniques. We knew from a lot of careful studies by the LIGO and Virgo detector characterization teams, we have a group of people whose job it is to look at the data coming out of the detectors and to understand these non-Gaussian noise transients that happen in the detector data. And so this group looked at this noise transient and realized very quickly that it was a saturation of a kind that they'd seen before. So they were very confident very quickly that this was a class of glitches that had been seen and observed before in the LIGO Livingston detector, and that we just got unlucky that this glitch happened right towards the end of the signal. In fact, the glitch isn't as bad as it looks here. The width of the glitch here is partly because of the filters that are used to make these time-frequency spectrograms. The duration of the glitch itself is very short. This blue curve here shows a fit to the glitch made using a wavelet fit to the glitch that was then later used to subtract it. But what we did in low latency to get something out very quickly is we just said, OK, we have a known class of glitch right here in the detector data. We'll just zero out the detector data, just with a nice smooth hand window, roll off the detector data, and then just push this through the search algorithms again and see if they actually then find a signaling coincidence. So they won't throw something out by having a glitch towards the end of the signal. And then later on, for more careful follow-up, we did a more careful subtraction, but this is what we did to get the sky localization out. So we did this, we reanalyzed this with a piece of software called PyCVC. This is one of our other search pipelines developed primarily by my group in Syracuse and the AI groups of Bruce Allen and Alessandra. So we did a rapid offline reanalysis of the Hanford, Livingston, and Virgo data. This is the time from the what came the putative event time in seconds and the signal to noise ratio. And now when you reanalyze it, the searches are finding nice loud signals. The blue trace here is the Hanford detector, so it has an SNR of about 15 in Hanford. And then the SNR in Livingston is actually much higher. It's almost 25 in the Livingston detector. And these dotted lines here show the expected time delay between Hanford and Livingston and the Virgo detector. So this green line right here shows the signal to noise in the Virgo detector. And what you can see is you have a very loud signal in Livingston, very loud signal in Hanford, and then nothing very much within this, this time window to the Virgo detector. And as Lisa said earlier, Virgo is a bit less sensitive than the LIGO detectors, but it's not that much less sensitive. You would expect to see something this loud in the Virgo detectors. There is a difference in the LIGO sensitivity and the Virgo sensitivity, but the difference in relative sensitivities, you know, if it's this loud in Livingston, you should be able to see something in the Virgo detector. However, gravitational wave detectors are not omnidirectional. They are not equally sensitive to the sky in all directions. They have a beam pattern where they're most sensitive directly above the detector and directly below the detector, where you get the most stretching and squeezing in the arms as you get the gravitational wave passing through. And they're least sensitive come along the diagonal arms of the detector. So you end up with a beam pattern for the detectors that looks kind of like a peanut. And you can tell from the relative sensitivity of the detectors and from the SNR you see in Hanford and Livingston, it turns out that this source came in a place which wasn't exactly at the Virgo dead spot, but was quite close to the Virgo dead spot. And so the absence of a signal in the Virgo detector is actually quite constraining to the sky localization. So the fact you see it in Hanford and Livingston and you don't see anything at all within this window is very constraining in the sky location. So it really was the network of LIGO, Hanford, LIGO, Livingston, and Virgo that gave us the very accurate sky localization for this signal. So just some credit to some of the people in the DETCHAR group and the search group who react very quickly to this. Laura and Andy are two of the leading lights in DETCHAR. And then Tito, Ian, Alex, and TJ reacted very quickly to this to get the signal reprocessed and get the SNR time series, which is what's needed to do the sky localization. And then this was passed into Leo Singer's nice package called Baystar that takes the signal to noise time series from the search and gets a sky localization on the detector data. So this is the sky localization that went out, this region right here, this is the Hanford-Livingston-Virgo sky localization, went out with a distance estimate. So the distance estimate is very close, around 40 megaparsecs, and a very small sky region, and that went out to the astronomy partners so they could actually start searching for it. And so this went out around 1331, so new sky map from Vaystar. Sucks for Virgo, it's in their dead spot. It's not quite in their dead spot, it's close to their dead spot. And the reaction from the astronomy community was, this is an amazing localization. And it truly was. This is much better than I thought we would get in the first years of the Advanced LIGO Virgo network. So here's the official notification. Went out at 1:54 p.m. EDT with the sky localization. So preliminary offline analysis of the candidate identified in low latency by GST Lao. This contained all the sky localization that went out to the EM community. And this is the image from the DCAM collaboration of the GW170817, the kilonova signature right here. This is the image from half a day to 1.5 days post-merger, and then this is 14 days post-merger where the optical image has faded away. And there'll be more talks about this tomorrow. One thing as well, let's come back to the gamma ray burst that happened 2 seconds afterwards. So this is a nice plot from the paper we wrote with the Fermi and integral teams that shows the gravitational wave time frequency map here. So time on the x-axis, gravitational wave frequency here. And then this is the signal from the Fermi GBM detectors and the 2 different energy bands and the integral detector. So this is the merger time right here as measured using these templated searches. And then this is the start of the GRB right here. And the probability of seeing a GRB, Fermi and integral localize the GRB on the sky as well, although not as well as LIGO and Virgo do, but we have a temporal and spatial coincidence. The sky's a big place, we have a long time to observe. The chance of this happening just by chance is excluded at the 5 sigma level. So this is a great result that confirms that binary neutron star mergers are the progenitors at least one, possibly many, there may be neutron star black holes as well, but GRBs are the progenitors of this short-hard gamma ray burst. And we have a nice accurate time delay, 1.74 seconds, between the end of the gravitational wave signal and the start of the gamma ray burst, with a lot of physics happening in there that we can explore with future detectors, hopefully. As we get more sensitive, we can start to see post-merger signatures. Once you get up here, what the post-merger is basically buried in the noise in these detectors. But as Matt said, as we get further up here, we can maybe explore some of these post-merger gravitational wave signatures with future detectors. So this is what the fully clean detector data looks like from the discovery paper. So this is a time frequency spectrogram again here. This is the Virgo detector. There's not much of a signal here in Virgo. Here in LIGO Livingston, you have this nice long track, almost 30 seconds, where the signal is visible in the detector data. And this is the LIGO Hanford detector, a little bit less sensitive. This is fully glitch-removed clean data. So this is the best we can do. This uses Jenny Drigger's glitch cleaning process that Lisa talked about earlier, where auxiliary noises are subtracted from the detector data, and maybe Neil will talk about this later, but the removal of this Bayesian fit to the glitch to do a more accurate excision of just the glitch from the detector data rather than the brute force, let's zero out the data and get something quickly out to the astronomy community. So this is the beautiful, clean data set that was released alongside the discovery paper that was published in PRL. So, let me switch gears a little bit. So I set out about 19 years ago to discover binary neutron stars. Bruce Allen, who I started grad school with, said, you could be the graduate student who discovers gravitational waves from neutron star mergers. Just didn't tell me it would be 20 years before it happened. So this is one of the last LIGO papers I wrote. So after this, my group decided that LIGO is very good about releasing their data openly. LIGO has an agreement with the National Science Foundation to release an hour of data around the time of all the discoveries when the papers are published. So this data is freely available to use. And in fact, the full 01 data set has been released. So the full 01 observing run data set has been released. And so if you want to search for crazy things like boson stars or cosmic strings or something that LIGO hasn't searched for yet in the 01 data, you can actually download the data set and you can search for it. So what I'll talk about in the second half of the talk is some results we have putting EM observations and nuclear physics together with this LIGO data, with the LIGO and Virgo data. And the way we do this, I'll just show this very briefly, but there'll be more talks this afternoon. With Bayes' theorem, so we use Bayesian parameter estimation and model selection to look at the data. So we get the data from LOSC, the LIGO Open Science Center. We need models that Alessandra talked about. So if we have waveform models that are parameterized by the intrinsic parameters of the binary signal, we need likelihood functions that tell us we assume the LIGO Virgo data is Gaussian, so we use the standard match filter likelihood and the detector data that basically just correlates our model with the detector data weighted by the sensitivity of the noise curve. And we need priors, marginalization, visualization software, and all this type of stuff. So one plug I'll give you is if you're interested in doing this stuff yourself on the open data, there's a software package called PyCBC. It's available at pycbc.org. It's primarily developed by the Syracuse and AEI groups. There's an open source package for doing this type of visualization, data analysis, all this type of stuff. And Chris, Colin, and Alex are the primary developers of this. They've put a lot of effort into the search code and also more recently into parameter estimation code. So a couple of results that we have from combining the gravitational wave data with data from other observatories. So as Alessandra talked about earlier, there's a degeneracy between the luminosity distance to a binary and the inclination angle of the binary. So a binary that's face on will appear twice as loud as the same binary that is edge on, because you see both polarizations of the gravitational wave. And that distance translates to a degeneracy between the inclination and the luminosity distance. But recently, there's been this very nice paper from Cantiello et al., which used surface brightness fluctuations of NGC 4993, the host galaxy of GW 170817. Basically look at the power spectral density of these fluctuations as a standard calibrated distance ladder to get a very precise measure of the distance of the galaxy. And they measured this at 40.7 plus or minus 2.36 megaparsecs. So what we did, Ido, my graduate students, myself, we took this data. We took the LIGO and Virgo data from LOSC, the PyCBC parameter estimation software from Chris Beer, Colin Capano et al., used the MC Markov chain Monte Carlo sampler from Foreman et al. We put all this together, and Daniel Finstad's the graduate student who did the work, and we basically got posteriors for the measurement of the inclination angle of the binary, where we used the precise measurement of the luminosity distance of the host galaxy as a prior on the distance. So let me zoom in onto the corner plot here. So this basically shows the luminosity distance here, and then the marginalized inclination angle right here. Elia did a nice paper on this where he used the H0 measurement. We used the distance measurement directly. And so you can see when we put in this the distance measure we got from the EM observations is right here. The gravitational waves really aren't informative. We get the same posterior out as we put in on the prior and the distance. But we get a much tighter constraint on the inclination angle of the binary right here, and so we get a better measurement on the inclination angle, including a lower constraint because we tried a few different priors to let us test the lower constraints. The viewing angle of the binary we estimated to be 32 plus 10 minus 13 with a statistical error with a systematic error of about 1.7 degrees. And we tried a bunch of different choices of prior to make sure it's robust with lower limit of about greater than 13 degrees for the viewing angle of the binary. And if people are interested in experimenting with this, we used open data in. We have open data going out. So we released all of our posteriors for the parameter estimation. So if people want to take these posteriors and use them as priors in some other analysis, we've made them all public on GitHub, so they're all publicly available. And we have instructions for grabbing these data and playing with them, so you can take our data and you can run with it and do something else. One other result I'll just point to briefly in the last couple of minutes is we looked at measuring the nuclear equation of state with these binaries. So this is a nice plot from a paper by Roland Haas that shows a numerical simulation of a binary neutron star merger, and you can see that these binary neutron stars are tidally deformed by the gravity of the other star. And so as these binaries are merging around each other, in the standard point mass approximation that we use in post-Newtonian theory, you just have 2 point masses going around each other, but really these are fluid bodies, and the amount of tidal deformation they experience depends on the nuclear equation of state, the equation of state of these two neutron stars. And so it depends on the equation of state that goes into this tidal deformability lambda. The way this enters the gravitational waveform is this parameter lambda tilde. You can think of this as, as if I had 2 point objects inspiraling, it's the time-changing quadrupole moment that determines the inspiral rate. If my neutron stars are deformed and take on a more cigar shape rather than being round, I have more time-changing quadrupole moments, I have more tidal deformability, I in-spiral more quickly. So that's basically how it enters into the gravitational waveform. So one thing we did to compare against the LIGO-Virgo results is the LIGO-Virgo results didn't place any priors on the stars themselves. They assumed that the stars could have different equation of states. You could have a black hole and a neutron star. So there's no prior placed on the structure of the two objects. We said, okay, so let's treat these things. Let's have our model be that these two things are neutron stars. And Jim Latimer did a bunch of simulations where he looked at, different nuclear equation of states and found the punchline of this is that in the mass range of interest for the masses for GW 170817, you might not know what the radius of the neutron star is. It depends on the nuclear equation of state, but there's very little change in the radius as you shift around the plausible masses for the two neutron stars here. So what you can do is you can impose a common equation of state constraint where we said, we don't know what the equation of state is, but let's assume that both neutron stars have a nuclear equation of state that's basically the same equation of state. So we don't know what the radius is, but we'll assume that the radius is basically the same. And we tried a few different things out. This is just justifying the equation of state constraint. We tried a few different mass priors, because there's been papers by Agathos et al. That said that the measurement of the EOS depends on the mass priors. So we tried a few different mass priors. And these are our results basically for the radius of the neutron star. Shomi Day is a grad student who led this work. This is the tidal deformability and the radius of the neutron star. Pretty robust to all three mass distributions that we used. Nice measurement of the equation state of the neutron star, so between 8.8 kilometers and 14.1 kilometers. And again, all of this is public on GitHub. So I will stop there. Okay, thank you.
Well, thanks for sharing the dirty data.
What did you assume for the prior for neutron star masses?
So we used three. Let me go back a couple of slides. So we used three different priors on the neutron star masses. So there's a paper by Agathos et al. Where they looked into a couple of different priors. What we did was we basically ran the analysis 3 times. One with a uniform distribution, so just uniform between 1 and 2. Then there's a paper by Ozel, a review paper where they have a fit to both the masses of neutron stars seen in double neutron star systems in radio, and then all neutron stars. One is a fairly finely peaked Gaussian, the other are a double hump distribution. And so we basically ran with all of those 3 priors on the masses of the neutron stars, and the tidal deformability and the radius results are within the statistical errors. So the choice of prior doesn't really affect our results significantly. Or the choice of prior on the masses. So from the gravitational waves, you really can't conclude very much, because as you don't even really see the very last parts of the merger very well. So binary neutron star system coalesces around 1500 hertz. And so the signal really disappears. The noise curve is rising at high frequencies. And so the signal disappears into the noise around, above a kilohertz. So you don't get any signal from the gravitational waves at high frequencies. Really, you then need the EM observations and say, okay, what happened afterwards? And we don't have very early EM observations. The EM observations came later, and so a lot of what happened after the merger and forming a black hole is theory that's trying to piece together the picture from the gravitational waves at lower frequencies, the equation of state measurements, and then what people saw in terms of the red-blue kilonova model that was seen afterwards. So I think Brian is maybe, I think someone will talk about this maybe in a bit more detail.
Yeah, I think that the amount of the detector was just much larger than you would expect based on simulations and what it's compromised. So I think most people believe that. And also the colors indicate that something was strongly rated by the tree number, which will scale. So I think the indications of that it survived. That it's a definitive proof.
But we need more sensitivity to get, or louder signals to get the post-merger signatures.
I think you have to clarify. You don't mean survive indefinitely. You mean
Yeah,
survive for a period.
Yeah, survive for it, yeah. Yeah, yeah.
So the equation of state part is something that's driving a lot of the improvement at high frequency, and this was a nearby very significant event. Do you have a sense of how much of an improvement, or how much closer by an event we needed to narrow this down to start actually ruling out families of equations?
That we're looking into right now. That, and particularly, it's not just closer, but as we get towards design sensitivity, what can we do? There's been a bunch of the Agathos paper, I think, is a nice paper where they looked at populations of binary neutron stars, and it's always dominated by the lattice one you get, right? They did this stacking technique, and I think Prayesh Kumar looked at this for neutron star black hole binaries, and you see this increase in constraining the equation of state parameters, and all these plots you will see a big jump when you get the loudest one. I don't know off the top of my head what loudest has to be to really pin this down precisely. Matt?
I think people within a factor of 2 or 3 or 1.
Or something like this.
Yeah.
If there is time, I can make a comment.
All right, last question.
Not so much a question, but a thought related to Matt's presentation from earlier. I mean, assuming in the next, decade or so, we don't get lucky enough, and with just the kind of improvements that have been looked at with the detectors to really nail down the equation of state. I mean, thinking of a dedicated design instrument that really focuses on sensitivity and high frequency, Spectra, the post-merger phase, the science is compelling enough to make it go into that. Obviously, you need the regular detectors perhaps to capture the signal in the first place, but something that really goes after the post-merger, gets all that detail flows.
Yeah, that's one of the things. So Matt and I and Stefan Balmer and Safi and others just put in a proposal to scope out third-generation detectors in the US study, and one of the things we want to look at is the network, right? It's not just having a network to get sky localization, it's having a network to get the physics, right? That in a surface facility, you can say, okay, I'll give up on the low frequency and I'll go really deep in the high frequency. Something underground or more expensive might get you something else. So there's steps you can take if we're not yet at full Cosmic Explorer, factor of 100 all the way across the band.
Okay,